All right, good morning, Algebra 2. Today we're going to talk about natural logarithms, which I don't want you to get too freaked out about these because they are actually very much like our common logarithms that we were talking about before. So whereas our common logarithms we had a base of 10, our natural logarithms are going to have a base of e. And remember, e was just Euler's number, and it was that 2.718, 718, etc., number. So it's just a different base. That's all we're doing, okay? And since it's Euler's number, we say it's natural logarithms. I'm not really sure where the name natural came from, but we'll go with it, okay? So ignore all this for right now. And actually, I just want to draw a parallel between our old log base 10 of x. We could write that as log of x. And we said, okay, if we don't see anything here, we would assume it's a base 10, okay? Because those are the most common, which is why they call those common logarithms. Now, for our log base e of x, now, we can't just drop the e. These are also fairly common, so we can't just drop the e because then it would look just like this, which would be a problem because we wouldn't know, is it 10 or is it e? So what they did was they said instead of with log of x here, we'll say ln of x, which is supposed to stand for natural log of x. So don't read ln of an x. Read it as its name, so it's natural log of x, okay? And they work the same way. So if you have your natural log of m equals n, remember we could rearrange this in exponent form. There's not really a base e here written, but we can assume that there was one in here, just like it was here. So we would remember take n and put it on our base. So we'd have e to the nth power equals, and then m would have to bump out this way. So e to the nth power, which is exactly what we would get, equals m over here. Okay, so it's the same idea. We just, when we see that natural log of x, we can assume there's a base e and take whatever it is out here to the exponent, all right, and bump the x out this way, all right? So same thing, we just now have a base of e. Okay, so let's take a look. I actually have the graphs drawn out here for us. It says just as the function with equation y equals log of x is the inverse function of y equals 10 to the x power, which is exactly what we talked about in the last video. Similarly, y equals the natural log of x is the inverse of y equals e to the x power. So it's just the exponent, but with our new base of e here instead of the 10 that we had before. Okay, so these guys are inverses of each other. Their graphs are really, really similar to the ones of log of x and 10 to the x power. So if you look here, this red line is y equals e to the x power. So this is our exponential equation. This line y equals x is just to show the reflection, and then this line here, y equals the natural log of x, is our log function. All right, so again, they have the same properties, and what you know is true for exponents, the opposite is going to be true for the natural log. Okay, so you can see the graph of each function is the reflection image of the other over the line with equation y equals x, which means they are inverses. We know this from the last chapter. Okay, example 1 says, ignoring the force of gravity, the maximum velocity v of a rocket is given by the formula v equals c times the natural log of r. So I'm just going to box that up because we're probably going to use that, where c is the velocity of the exhaust and r is the ratio of the mass of the rocket fuel, or of the rocket with fuel to its mass without fuel. Okay, so it's when it has a full tank and when it has an empty tank. So to achieve a stable orbit of 160 kilometers above Earth, a spacecraft must attain a velocity of about 7.8 kilometers per second. So I'm also going to underline those numbers because typically numbers are important when we're doing a math problem. Okay, I know this is kind of a lot to take in, but no, we have our formula here. This v is for velocity. The c is the velocity of the exhaust, and then the natural log r is our ratio of the rocket with fuel versus the rocket without fuel. Okay, so those are what all our variables are. Okay, so letter A says, with a small payload, a solid propellant rocket could have a mass ratio of about 19. A typical exhaust velocity for such a rocket might be about 2.4 kilometers per second. Could a spacecraft propelled by this rocket achieve a stable orbit? So that's the question we want to answer. It's going to be a yes or no question. And we're going to ignore B for right now because we're only answering A. And I've taken all of our important information and copied it onto the next page. Hopefully you've copied this example already. Okay, so our formula we have is V equals C times the natural log of R. Our orbit is 160 kilometers above Earth, and we must attain a velocity of 7.8 kilometers per second. And our mass ratio was 19, and our exhaust velocity is 2.4 kilometers per second. Okay, so we've got a lot of numbers going on here, but the orbit is just something we're trying to sustain here. So these numbers are going to kind of, I don't want to say ignore, but kind of put to the side for right now, because our particular situation tells us that the mass ratio is 19 and the exhaust velocity is 2.4 kilometers per second. Our goal is to get to what we have here for our orbit. So this is really, these are our goal numbers here, okay? But our actual numbers that we're going to use for our equation are these two right here. So our velocity is v. We don't know that yet. We're trying to figure that out. Our exhaust velocity, remember, was c here, and that's 2.4. So we say 2.4 times the natural log. Oops. Sorry. Try that again. Okay. Okay, so the, times the natural log, there we go, of r. And remember, r was our ratio from our tank of gas being full to our tank of gas being empty. That would be 19 here, so the natural log of 19. Okay, so this allows us, by plugging it into this formula, it allows us to figure out what our actual velocity is going to be, and we're hoping that it's at least 7.8 so that we can stay 150 or 160 kilometers above the Earth. So let's see here. So we do 2.4, clear out our calculator, 2.4, oh my goodness, 2.4 times the natural log. Now natural log is the E button, but we don't have to hit second, so we just say natural log of 19. And then we say okay. Let's see what that is. 7.07 essentially is what that is. So thank you, calculator, but we're done with you. Okay, so 7.07 kilometers per second. And that is the actual velocity that a rocket such with these parameters would actually emit. So that's our new velocity. Is it enough to keep our space rocket in orbit? Well, we have to hit 7.8, and 7.07 is close, but it's not quite there. So would this actually be able to launch a rocket into space? We'd say no, the velocity is not great enough. So we would not be able to sustain ourselves at an orbit of 160 kilometers above Earth. Okay, so not going to work out for us, which is a good thing to know, especially if you work at NASA. It's definitely a good thing to know, because you don't just shoot off rockets and hope and cross your fingers that they get to where they need to get to. You really do have to know what's going on. So they would do these equations and they'd say, no, it's not good enough, so we have to change something. We do have to change the mass ratio or the exhaust velocity, and they would do that before they launch the rocket, therefore ensuring they don't kill anybody or, you know, have rockets exploding in the sky. Your calculations have to be pretty precise when you're working for NASA. Okay, part B says find R for a rocket if C equals 1963 meters per second and V equals 2021 meters per second. So we're going to go grab our formula. It's, remember, V equals C times the natural log of R. So I'm just going to write that down here. So V equals C times the natural log of R. And they want us to find the ratio. This is, remember, our ratio. So this is like saying, okay, well, we can work backwards and figure out what we need to have our rocket weighing before fuel and after fuel. So we're actually going to be working backwards here. We're finding R. We know C and we know V. So V's going in for V. So 2021. And then C is going to be 1963 times the natural log of R. And we're trying to figure out what the natural log of R is. Okay, so first step is to divide by 1963. Because we're trying to get to R here, so 1963. Over here they cancel. We have the natural log of R equals, and let's do our arithmetic here. So 2021 divided by 1963. Okay, and we get 1.03 is what that would be. And we'll get rid of that for a second. because we used to not be able to solve these, but now that we know about logarithms, we actually can. Remember, this is base e, so what we're going to do is we're going to take this 1.03, we're going to write it in exponential form, so we're going to say 1.03 gets put on e, so e to the 1.03, and remember, r gets bumped out this way, equals r. So now we just need to do e to the 1.03 power, and that'll give us our r, which I'm going to put right over here. So, alright. Okay, e, remember we have to hit second and the natural log key. And then we could type in 1.03, but remember from the last example that was actually giving us a rounded answer. So we're actually going to pull this, so hit second answer so that it's as accurate as we can possibly be, because remember, we're working for NASA. They don't want us to round at all, because that could kill people, literally. Okay, so then we hit enter, and we get 2.7998. Okay, but we don't need to round quite that far out, so we'll just round it to 2 places, which means what's going to happen here is this 9 is going to bump this 9 up to the 10, so we're going to get r equals 2.80. Okay, so 2.80, remembering what our units were, oh, that's a ratio, I'm sorry, so our ratio is 2.80. That actually doesn't have units. Okay, so our ratio of a rocket with a full tank to a rocket with an empty tank is 2.80, which, quite honestly, I don't know if that's good or bad because I don't work at NASA, but I'm sure this number would mean something to them. Now, if we compare it to our last problem, we had a mass ratio of 19, and now we have a ratio of, now we have a ratio of 2.8. I don't know, those numbers are too far apart for me to be comfortable anyway. So I'm thinking this is either really good or not good, depending on what our other problem was. So I guess we'll never know unless somebody knows somebody who works at NASA. Okay, we have a few more examples to get through, so I'm going to go ahead and pause this video, and hopefully you'll join me for the next one so we can get through the rest of our natural logs. See you in a bit.